AP Chemsters, this is Mrs. Vanderwall, and do I have a sweet lesson for you today in our next edition of the Blankwall presentation. So what are you looking at? You are looking at a jar of rock candy. And if you've ever made rock candy before, you know you make a supersaturated sugar solution and pour it in a jar or whatever, and then you have a paper clip probably tied to a string so that the rock candy has some kind of a surface to adhere to. And if you were to cap this, you would know that you could make the candy and you'd keep the water from evaporating. And this jar is probably about 8 years old, so let's not even talk about let's having some of this. You can do this at home if you want, though. You can eat it there. So my question to you is, what is going on in this jar? Is there actually movement going on? Is it dynamic or is it a static situation? Well, you probably guessed by now that it's a dynamic situation. What if I could look at my microscope and look at the individual sugar crystals, I would notice that there are some of the solid sugars, the rock candy, being dissolved in this water. And what else is going on? Well, the sugar crystals that have been dissolved can recrystallize back into the solid. And when we hit that equilibrium where the rates are equal, the rate of dissolving equals the rate of recrystallization, we have a dynamic equilibrium. And that's what this chapter is all about. So why don't you get out your notes and go to section 15.6 and we will begin. So section 15.6 is about solubility equilibria, there we go, and the solubility product, otherwise known as KSP. So when you ever have a solid in water, you will set up a dynamic equilibrium. Dynamic means moving, motion. There is something going on. It's just not sitting there. And so back in the early sections of AP, way back in September, we were talking about the solubility rules, and we said how some things are insoluble and things are soluble. And that's really what we're talking about. But when we said that things are insoluble, we didn't even talk about KSP at this point. That in actuality, certain ionic salts are in fact, they're all soluble, only to a certain extent. So what we would consider insoluble is where the equilibrium lies far to the direction of where your solid is. So only a very, very small amount is indeed dissolving. So let's take a look at the case of the calcium fluoride. So the very first equation where CaF2 solid is going to the ions, that is your dissolving process. And then the second equation where your calcium ion and your fluoride ion are coming back into the solid, that is your crystallizing process. And so when the rates of dissolving and the rates of crystallizing are the same, we say we are in equilibrium. So notice the double arrow. When you have a double arrow, we say it's an equilibrium, and that's where the rate of dissolving will equal the rate of crystallization. So here's actually a nice little picture of what's going on here. We have the salt is initially put in the water, and the only thing that's going to happen is the dissolving process because you have no ions in solution. So then what? Once you get some ions in solution, some of those ions can recrystallize back into the solid again. And eventually, you are going to get this equilibrium set up in the third picture, where you have that the rate of dissolving, so the arrows going out like this, these guys here, they are dissolving at the same rate as the crystallizing occurs. So notice that you have the same number of arrows going out as you have the arrows going in. So the rates are equal. That will be your equilibria setup here for KSP. So let's talk about this. So we're going back to the same calcium fluoride setup here. Notice that we will set up an equilibrium constant called KSP. And how do you set it up? Well, things that are aqueous, the things that have molarities, are in the expression, but notice that the solid over here is not in the expression. This is just like what we learned in chapter 13. We haven't seen this much when we were in chapter 14 and the early parts of 15, because we were working with the weak acids and weak bases, and their coefficients were always 1, and there were no solids present. So we're kind of back to this idea of what goes in the equilibrium expression. Now note one other thing when we wrote this KSP out. So you see the coefficient of the fluoride ion. Do you remember back in chapter 13, what did we have to do when you had a coefficient? You had to square the concentrations. Okay, so again, it says it's just like any equilibrium expression, just like what we did in chapter 13, nothing new. So let's talk about a couple definitions. So first of all, what is solubility? Well, in this section, we will define solubility as the number of moles that are dissolved from the solid in 1 liter solution. So let me write that. All right, so the solubility here I wrote down is defined as the moles of your solid dissolved in 1 liter solution. Well, does that ring a bell? What is moles per liter equal to? That's your molarity. That is your concentrations up here. And it says you can experimentally determine the solubility of the ionic solid to calculate KSP. So once we know what the solubility is, how many moles of the solid were dissolved, you can then figure out these concentrations, and therefore you can figure out the KSP. So let's check out problem number 10. They're asking us to do that. Notice it says copper 1 bromide has a measured solubility of 2.0 times 10 to the negative 4th moles per liter. That is the number of moles of the copper bromide solid that has been dissolved. So what are we going to set up? Let's set up an ice table because it is an equilibrium setup, so you use an ice table. Go ahead and write down your equation right now. Well, hopefully you got this far where you dissolve the copper 1 bromide into its ions, and notice that their coefficients are 1 and 1. Look at your formula, and that's how you dissolve it. Now to finish off the ice table, at least to start it, what is the initial concentration of copper 1 bromide? And that's a funny question. Can you have an initial concentration of copper 1 bromide? It's a solid. There is no concentration, so don't worry about it. If you want to, just think of it in excess. You have lots of the solid there, but you cannot talk about its molarity because it's a solid. But you can talk about the initial concentration of the copper and the bromide. Go back up here again. How many ions are initially present in this beaker? And the answer is 0. Okay, so now what? Well, what is solubility? That is your X. Your X is solubility. Please know that. So how many moles in 1 liter does the copper bromide dissolve? Well, X. That's how many moles of copper bromide will dissolve in 1 liter of solution. And now we can say, well, how many moles of copper ion will be formed? X. How many bromide? X. All right, so at equilibrium, how much copper bromide do I have? I don't have a molarity. You can't really answer that. But, excuse me, can you talk about how many ions of copper you have and how many ions of bromide you have? Yes, so you can talk about its equilibrium concentration. Okay, so now what? We can set up the KSP value. So KSP is, excuse me, is equal to the copper ion concentration times the bromide concentration. I'll write that down. Well, what is X? X is the solubility. That's the number they gave us. That is your 2.0 times 10 to the negative 4th. That is your X. So let's plug those in. Multiply. And that is the KSP value. Now notice I got lazy. No, I didn't put any units down. And normally we don't put any units for KSP. They could ask us the units. It'd be molarity squared, but you never ever see units on KSP. Now look at this problem and now turn the page to the next problem. What is different between the copper 1 bromide and the bismuth sulfide? Well, the main difference is you're going to have coefficients. So go ahead on your own, write down the equation of the bismuth sulfide dissolving. All right, did you write that down? Don't forget these coefficients because that is really important. So now we're going to set up our ice table again, just like what we did before. And once again, we cannot talk about the molarity of the solid. There is no, molarity. It's a solid. You can't do that. But you can talk about how much the initial bismuth ion you have and initial sulfide ion you have, and they're both zeros. Now, what did we define X as? X is your solubility of the bismuth sulfide. How many moles of bismuth sulfide can be dissolved in 1 liter? So you have 1 bismuth sulfide, but how many moles of bismuth ion will you make from 1 mole of the bismuth sulfide? You're going to make 2 moles. You're going to have a ratio of 2 moles of bismuth ion to 1 mole of bismuth sulfide solid. And notice what's going to happen with the sulfide. You're going to have 3 moles. Okay, so there you go. And now we can set up and calculate the KSP. So you do that. Well, I erase my board because I'm running out of room. So hopefully you're writing small enough. So I'm going to pause this, rewrite it, and pick up where we left off. All right, notice how I wrote my KSP value. It was bismuth ion squared, because that's its coefficient, times the sulfide ion cubed, because 3 was its coefficient. This is probably your next most important step, is talking about the concentrations. So watch, my concentration of the bismuth ion was 2x. My concentration of my sulfide ion was 3x. Let me write that down. And what's X? It's your solubility. That's your 1.0 times 10 to the negative 15th. Let me do that. Okay, keep working on your math. Oops. All right, so how did I get those numbers? Well, 2 squared is 4, 10 to the 15th, negative 15 squared is negative 30th. Now watch, what is 3 cubed? It's not 9, it's 27 times 10 to the negative 45. And then when I use my calculator and I do all this work, you should end up with 1.1 times 10 to the negative 75, I believe. All right, and so I think, or is it 73? Let me look. Oh, sorry, it's 73. Whoops. And that's your answer. That's your KSP. Notice that number is really a bizarre looking number. Why is it such a negative number? It's because you have 5 ions in solution. So, you're going to take that 1.0 times 10 to the negative 15th and at least raise it to the 5th power for that, and then plus your other numbers as well. So that is a crazy number if you look. So let's try to do one more problem. We have 1.5 more minutes left, and then this is where actually I want to quit, is problem number 12, and then I'm done for the day. Notice what we're given here. We are given the KSP value of the copper 2 iodate, and you are asking to solve for its solubility. What are you asking for? You're asking to solve for X. So go ahead and set up your problem and see how you do. All right, so problem number 12, did you write down your equation? It's always important to do that so you know what ratio you're talking about. And I kind of skipped the ICE part because what's important here is that you have X number of copper ions and you have 2X number of the iodate ions. So then they gave you the KSP. And notice what you have to do. You just have to take the concentration of the copper ion, but you have to take the concentration of the iodate ion squared. You are looking for X. You are looking for the solubility. So I have X times 2X squared, and that's 4X cubed. Then I started running out of room here. So 1.4 times 10 to the negative 7th equals 4X cubed. Divided side by 4, you got 3.5 times 10 to the negative 8 is X cubed, and X equals 3.3 times 10 to the negative 3. That's your X. That's your solubility. that's what you're calculating for. Well, I hope you enjoyed this sweet lesson. Thanks again for listening. And Danny, I'll see you later.